Hello, young scholars. This video is a short, hopefully, tutorial on Newton's third law, which is simultaneously the most well-known but the least understood of Newton's three laws. First, let's see where we're at. So we learned from Newton's first law that not an object's velocity cannot change unless acted upon by we learned that it was a net force that causes an object's velocity to change. So its vector velocity will not change unless a net force is present, and then the velocity will definitely change. And in his second law, he said it was an equation, and the equation said that the net force is equal to the mass times acceleration. You can see that in his second law, he essentially mathematicized his first law. Velocity's changing. Hey, that's acceleration. Net forces cause changes in velocity. Net forces cause accelerations. And so his first and second laws are really a restating of the same idea. You'll notice there's a little extra blank here that we'll fill in a bit. His third law seems to go off in some other direction, and it's the one that everybody knows. And I'll start it off, see if in your mind you can finish it. For every action, ... For every action, there is an equal and opposite reaction. So this is weird because it seems to not be even talking about the same thing that he was previously talking about in Newton's first and second laws. Here we're talking about velocity, changes in velocities and forces. Here we're talking about changes in velocities and forces. And now every action and reaction. The first thing to understand is that this phrasing of action and reaction is probably not what Newton really even said, and it's certainly not what he meant. His third law really speaks about forces, and what he intended, or what he actually probably said, was that for every force, there is an equal and opposite force. No exceptions. Not sooner or later there'll be a force, or maybe, or in most cases, or anything like that. For every single force, there's an equal and opposite force. So what is meant by that? Well, let's take a look at this. Here's an object, and let's say it has a force, let's say of 4 newtons acting on it. If there's a force that is equal, then it must also be 4 newtons long. And if it's opposite, it must be in the opposite direction. So that equal and opposite force is right there. 4 newtons here, 4 newtons there. And so Newton's claim is that forces come in pairs. The total number of forces in the universe has to be an even number. Every single force is paired all the time. But a couple of interesting things about those forces, a couple of requirements to make sure that you're really looking at this Newton third law pair. And so there are 2 tests to see for sure if you're looking at a Newton's third law pair. Let's take a look at those tests. Boom. The 2 tests for Newton's third law pairs are as follows. 1, the paired forces must be of the same type. What does this mean? It means that if you have a friction force that you're looking at, there must be somewhere another friction force. If it's a normal force, there must be somewhere another normal force. If it's a tension force, there must be somewhere another tension force. And if it's a gravity force we're talking about, then there has to be somewhere another gravity force pointing in the exact opposite direction, but the same size. The other test is that the paired forces must be acting on different objects. They can't be acting on the same object. So let's take a look right here at this box sitting on a table or on a floor. And if we wanted to talk about the forces that we see here, of course you can see with your force vision, we have a normal force pointing up, we have a gravity force pointing down, and it's clear that these two forces must be of the same size, because if the normal force were bigger, up into the air you would accelerate, and if the gravity force were bigger, down the table you would barrow. So these are exactly the same size, and they're in exactly opposite directions, equal and opposite. Are they Newton's third law, equal and opposites? Well, let's check the tests. Are they of the same type? Nope. Normal and gravity, two different types. And are they acting on different objects? Nope. They're acting on the same object. They're both acting on the box. So while just because two forces are equal and opposite doesn't guarantee that they're going to be Newton's third law pairs, but they become candidates at least, because they do have to be equal and opposite. I suppose that's another test for the third law pairs. They have to be equal and opposite. Okay, so let's take a look here. So what is the equal and opposite force of this normal force? Well, just as let's say the floor pushes up on the box pushes down with equal strength on the floor. So we should be able to imagine a normal force which is exactly the same size as the one above, but in an opposite direction. So the floor feels a force downward, the box feels a force upward. These two forces are exactly the same. Let's label that as a little normal force. We'll get to this gravity force in a little bit here, because there must be an equal and opposite one to that, which is weird. We can maybe start thinking about that, because Newton's saying that there must be an upward pointing gravity force. This one points down. Somewhere there must be a force of the same type. Remember, this is a gravity force, F sub g. Oops, F sub g. So there must be an upward pointing gravity force somewhere. We'll talk about that in a minute. So let's take a look at another pair of forces here. Here's a force. I don't know. Let's say it's 10 newtons. Let's say it's a tension force. I suppose is fine. And maybe there's a person pulling on it. But let's examine these two forces here on the string that connects these two boxes. That's a tension force pulling the small box to the right. That's another tension force pulling the big box to the left. And we've learned that the tension's the same everywhere within a string. Do these two forces satisfy the two tests? Let's check. They're of the same type. Check. And we know that they're equal and opposite from what we've learned about forces. Check. And they are acting on different objects, so it satisfies all three tests. Therefore, we are looking at Newton's third law pairs. Let's take a look at another situation. Actually, let's begin by slowly adding forces to this blue box. So we'll begin with a force, and let's say it's a tension force. And of course, something's causing that tension force. Maybe there's some kind of a hand pulling a string. So I'm going to draw the string here. Here's the string, and here's some kind of a hand. And the hand is pulling the box forward. That is indeed a tension force, so let's label it as such, tension force. But there must be a force which is equal and opposite to that. Let's see if we can find them as we go. So let's see, there is a force which is equal and opposite. It is on the hand of the same size, but in the exact opposite direction. So there it is, the Newton's third law pair. Let's take a look at let's say there's a friction force here. So the box is feeling a friction force to the left, perhaps a bit smaller than the tension force it feels. Let's say the tension force is dominating this little friction force, so the box is accelerating to the right, friction force here. But there must be a force which is equal and opposite to this friction force. Where is it? Well, we know exactly how big it is. We know that it's pointing to the right. the ground exerts a friction force on the box to the left. The box exerts a friction force on the ground to the right of the exact equal size. So the ground feels a friction force, the box feels a friction force, two different objects, same size force, same type of force. There's a normal force, of course, pointing upward from the surface, going straight upward. It's a normal force, and we've talked about this already. There's an equal and opposite normal force pointing down from the box on the ground. This one is ground on box. This one is box on ground, but exactly the same size. This business of box on ground, ground on box is actually kind of interesting. We can always describe Newton's third law pairs in the same way. This is earth on box, box on earth. This is hand on box. This is box on hand through a tension force. Now let's turn our attention to this tricky gravity force. We know that there's a gravity force pointing straight down. We know it's just as big as the normal force. There it is. There's a good old mg. Straight down. Pretty close to straight down. Let's label it mg. Somewhere, according to Newton, there is another gravity force that is exactly as big as that, but pointing upward. It's a bit of a puzzle exactly where that might be. But think about what the box is interacting with. What's pulling the box downward? It's the Earth. Earth pulls box down, but box pulls Earth up. I know that's not a perfectly straight line, but you get the idea. So that is the gravity force. I won't call it mg, let's call it fg. But these two forces, mg and fg, are exactly the same size. mg, fg. Same size forces. They must be, and these are the Newton's third law forces. Why do we care about Newton's third law? Well, it helps us see forces. And if you can see forces, then you can predict how things are going to move. For example, let's take a look at this situation with the two blocks, 2 kilograms, 5 kilograms, the little fingers pushing it forward with a force of 14 newtons. There will be a normal force in between the two boxes, but what do we know about that normal force? Well, the 2 pushes on the 5, but the 5 also pushes on the 2. Those are normal forces, equal and opposite, acting on different objects. Those are Newton's third law pairs. So even though we don't know what those normal forces are, we do know that they're the exact same size in an opposite direction. So in the x direction, we can choose a direction of our positive acceleration this way. Kind of obvious it has to be this way. And so we have 3 forces at play. The 14 Newton force this way, a negative normal force on, I guess I should be clear here, we're describing a system that is, that's the system we're describing here. So that's the mass. We have a 14 Newton force to the right, a minus normal force to the left, a positive normal force to the right, and together that has to equal the mass of our system, which is 7 times A. These normal forces, as you can see, must cancel. They're gone, and they do not affect the motion of the system. In fact, anytime you see forces that are entirely within your system, not coming from the outside like some gravity's coming from the outside, but the forces are entirely between the two objects that are within the system, you can be certain that there'll be a pair of forces which cancel because of Newton's third law. So we can cast these forces away for 2 reasons. 1, they're going to algebraically cancel anyway, and 2, they're internal forces. That's why we say that it's only external forces that cause acceleration. So it's F net external, ext, that cause acceleration. In this case, if we divide both sides by 7, we get the acceleration is equal to 2 meters per second squared. And now if we go back to our very first panel, boom, 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 we can say that an object's velocity cannot change unless acted upon by a net external force, and it's only the external forces that cause acceleration in a system. Internal forces, which are invariably Newton's third law forces, do not affect how the system accelerates. And there it is. Now your challenge is to see me. I'll give you a piece of paper. It'll have a few different diagrams on it. And your job is to draw the forces and, in a different color, the Newton's third law pairs. Hope you enjoyed this. See you later.